In a previous video clip, we looked at combining velocities, really adding velocities is what we were doing when we had motion in the x direction. So remember, we used Lorentz transformation, and you got an equation like this. And what I've done here is added these x subscripts to the velocities. U sub r, remember, is the velocity in the rocket frame. Our example was Bob here going with some velocity, and Alice is here, so I get her in the picture. Going with some velocity v with respect to Alice's frame of reference, and shot off an escape pod in his direction of motion with velocity u sub r compared to him. And we discovered then the velocity that Alice would observe the escape pod to go followed this equation here. And we did a few examples with that just to check out how it might work. And in particular, we saw that even though the two velocities here, the velocity of Bob with respect to Alice of his spaceship, and then plus the velocity of the escape pod, if they both added up so they were greater than c just by adding them together, this equation would be such that the result would never be greater than c in terms of what Alice observed in terms of the velocity of the pod. What we want to do now is do another case where what happens if Bob shoots it up maybe straight up or just perpendicularly off to the side here, and figure out what would Alice see in that situation. And interestingly enough, this will bring us back to the light clock that we were talking about recently. So here's the situation. Bob shoots it up at some velocity u sub r, and we'll use a subscript y to emphasize this as just in the y direction now. We could say it's the z direction, but we'll choose the y direction for that direction. And of course, definition of velocity, delta y sub r over delta t sub r. This is for Bob now. He says, how far does it go in the y direction, and what's the elapsed time for how far it's going in that direction? That's going to be the definition of the velocity. And so now let's write down a couple of equations actually for u sub ly. That's what we're after here. What does Alice observe the velocity in the y direction to be? So u sub ly here is going to be delta yl over delta tl, just by definition of the velocity. And this is why I, as a reminder, added the y and z components through a Lorentz transformation. Remember, they don't transform at all. They're the same. And so delta y sub l is going to be the same as delta y sub r. So this is going to be delta y sub r over delta t sub l. But that does change, of course, by our equation we used before. Remember, we could use deltas in here to indicate change of quantity. So we'll write that as delta y sub r on the top. And then delta t sub l, remember, is using the equation here, is going to be gamma times delta t sub r plus v over c squared delta x sub r. All right, again, these are the quantities that Bob is measuring. And we're assuming everything is constant velocity here. For those of you who've had some physics, you say, well, what if it's accelerating? Well, we're not dealing with that case here. And therefore, we can define velocity as simply change in, not change in direction, but the direction, elapsed direction, if you want, the direction covered divided by the elapsed time. So delta y sub r over this quantity here. Again, we'd like to simplify. We'd like to be able to get some of the u sub r rocket frame y components in here. And so let's pull out this delta t sub r, sort of like we did before, and see what happens here. So we have delta y sub r on the top still, and got a gamma here. The gammas don't cancel this time. And we're going to pull out a delta t sub r from that expression. So we've got delta t sub r times 1 plus v over c squared delta x sub r over delta t sub r. Okay, so delta t sub r times 1 is the delta t sub r. Delta t sub r plus this thing gives us that, because the delta t sub r's would cancel there, of course. But then this is a little strange here, because notice that we're doing an equation for the y component, but we've got some x components in here as well. Remember what this was? This is just the velocity of the pod in the x direction in the rocket frame. Okay, so we could write, in fact, just to remind ourselves here, u sub rx equals delta x sub r over delta t sub r by definition. Very good delta there. That's even a worse one. There we go. Okay, now. So But in our example here, note what happens up for Bob. Not what happens, but what is happening for Bob here. There is no velocity of the pod in the x direction. Remember, Bob's stationary as far as he's concerned. He's shooting the pod straight up as far as he's concerned, or straight off to the side. And therefore, there is no velocity in the x direction for this example. So in this example, this equals 0. No velocity of the pod in the x direction as far as Bob is concerned. And so that's nice, because this whole term then here is 0 for us. So this thing here turns into 0 for this case. And look at what we're left with here. Delta y sub r divided by delta t sub r, and also divided by gamma. Delta y sub r divided by delta t sub r, that's the velocity in the y direction for Bob in the rocket frame, u sub ry. So this simply becomes u sub r in the y direction divided by gamma. Okay? Now, we're going to come back to that in a minute, but let's do one other thing here too, just to make sure here, because for Bob it's going just straight up, right? But for Alice, Bob is moving that way. So Alice may, and probably will, and actually will observe that the pod is going to go up at an angle, because you do have the velocity of motion here of the spaceship involved. And so let's see if we can get that in here as well. So we'll squeeze it in right here. We just did that. And what we're going to do here, make a little room. So let's do u sub Lx. In fact, here's the formula we want to use right here. Don't have to rewrite it, because we already wrote it. And so in this case, u sub Rx, remember we just finished talking about it, I just erased it, that's 0, right? As far as Bob is concerned, no velocity in the x direction. So I get 0 plus v all over 1 plus, well again, u sub Rx is 0 to Bob in this example. Therefore, this whole thing is 0, so I just get 1 plus 0. And in fact, we did this example when we were talking about the transformation equations here for the velocity. This just gives us v. So there are two components as we talk about the velocity here for Alice. One component is just the velocity v in the x direction, because that's just the motion of the spaceship here. And the other component of the velocity in the y direction for Alice is u sub ry over gamma. So it is whatever velocity Bob sees, they're shooting up, then that's going to be divided by gamma. Note one very interesting thing here. Gamma is in the denominator. So as the velocity of light gets, not velocity of light, as the velocity of the pod shooting up here gets faster and faster, closer to the speed of light, remember what happens to gamma? Gamma gets close to infinity. And therefore, this whole thing, no matter how big this velocity is, this is like something divided by a very, very, very big number. This goes to 0. So this approaches 0 as v approaches c, or gamma, another way to say it, gamma approaches infinity. So that's very interesting, because what that's saying is no matter how fast Bob shoots up his escape pod, if his relative velocity is close to the speed of light, Alice sees almost no upward velocity at all. This is Alice's upward velocity in the y direction that she's observing. If gamma is very large, if Bob's velocity is very close to the speed of light, this whole thing goes to 0. And all she sees is the sideways motion from the x direction v. And the reason, I mentioned the light clock a minute ago, because remember, we did an example with the light clock where, of course, the light clock, so here's Bob's light clock, moving with velocity v in that direction. And of course, we saw from Alice's perspective, the light beam goes up here, and then, well, down there, so the light clock has to get a little farther over there. And we talked about, as v gets closer and closer to the speed of light, remember that, get the green in here again, that this light beam can never catch up to that upward mirror. Because if this gets close to c, then this light beam has to travel too far to the upward mirror, and by the time it essentially gets there, the mirror would be farther away. And in fact, as it gets very, very close to C, this triangle gets very, very elongated, and in fact, this light beam never gets up to that top mirror, and it's frozen. The light clock, as Alice would observe it, if Bob could go by at the speed of light, which he can't, but if he gets very, very close to it, it's almost like the light clock is frozen. It ticks very, very slowly. It's just a time dilation effect. Gamma is very large, and therefore Bob's clock ticks very slow. If you could actually reach the speed of light, it's frozen. And that's what this mathematics here is telling us, another way that we argued for qualitatively earlier, that I never put the green in here. But if this is the velocity of light, if we're going c here, and so it can get up here at c, but it never gets up to that top mirror, that's what this is telling us. It's saying if we can go at the velocity of light, if Bob could shoot, or if Bob could have a spaceship at the velocity v of light here, then this would be infinite, and Alice's observed velocity for the escape pod going up, no matter what the velocity of the escape pod was, would be 0 in the upper direction, and she'd just see the c factor going across there. So tells us another way. It's good to have these consistency checks here, because you could say, just to make the point in one other way here, this light clock is sort of like the escape pod if the escape pod, instead of being an escape pod, were just a beam of light going up in that direction. Make it squiggly for a beam of light here. A beam of light going up in that direction, c. That's exactly what the light clock is. For Bob's perspective, it's going up and down like that. And so that's like shooting light beam directly perpendicular to Bob. If he's traveling at velocity c, then what this is saying in this case is Alice never sees that light beam go up. She just sees Bob go this way, and the light clock is frozen in that instance. So an interesting confirmation of some of the other things we've done. This is one of those things sometimes it takes a while just to sort of mull it over, think about it, work through it, convince yourself of that it actually makes sense, put in some numbers, try things out, sort of get a feel for what's going on here.